The single biggest thing that scares people away from machine learning is the math. They picture a PhD, a wall of Greek symbols, years of proofs, and they quit before they even begin. So here is the truth. Said plainly, you need far less than you think. Not a degree. 3 pictures: space, chance, and change. Hold those 3 in your head, and the math behind all of AI stops being a wall and becomes something you can actually see. The math you genuinely use in data science is small, surprisingly small. It is not a 4-year degree crammed into a video. It is a handful of ideas, each with one clear mental picture. And the same few ideas keep turning up everywhere. In a simple spreadsheet, in a recommendation, and inside a giant language model. Learn the pictures once, and you will recognize them for the rest of your life. Here is why this matters more than a grade ever did. Anyone can import a library and call a function. But the people who truly build with AI can see what is happening underneath. Why a model works, why it suddenly breaks, and how to fix it. That X-ray vision is not genius. It is just these 3 pictures, held clearly. By the end of this video, they will be yours. So here is the entire toolkit on a single slide. Linear algebra, the language of space, for representing and transforming data. Statistics, the language of chance, for reasoning when you are not sure. And calculus, the language of change, for how a model actually improves. 3 languages of the world. You do not need the heavy machinery of any of them. You need the core intuition of each and the way they lock together. And here's the secret that ties this whole video together. These 3 do not live in separate boxes. They meet in one loop. You represent the data as space. You doubt it with probability. You improve by following the slope of change. Then you go around again. That single loop, turning, is every model in this entire series. Keep it in the back of your mind, because we are going to build right up to it, one piece at a time. Chapter 1. Vectors, where raw data quietly becomes space. Let us start at the very bottom, with the atom of all of this, the vector. Do not let the word scare you. A vector is just a list of numbers. A house is a vector: square footage, bedrooms, price. A user is a vector: age, clicks, money spent. Even a word becomes a vector, a list of numbers that captures its meaning. Anything you can describe with numbers becomes one, and in data science, that is everything. Now the move that changes how you see all of it. A list of 2 numbers is not only a list, it is a point in space. 3 and 2 means go 3 across, 2 up, and place a dot. The arrow from the origin out to that dot is the same vector. Now with a direction and a length. Numbers just became geometry. And geometry we can reason about with pictures. Zoom out, and your entire dataset becomes a cloud of points. Every row is one point. Every column is one axis. 8,000 customers, 8,000 points drifting in space. And the instant your data is a cloud, learning turns into geometry, finding its shape, its directions, and which points sit close to which. That single shift is the foundation of half of machine learning. But my data has 1,000 columns, you say. No problem at all. 8,000 numbers is simply a point in 1,000 dimensions. You cannot picture that. Truly, nobody can. But here is the gift. The math is identical to 2 dimensions. It is still just a list of coordinates. So reason in 2 dimensions, where your eyes work, and trust that every idea scales up untouched. It always does. And this one move quietly runs all of modern AI. An image becomes a list of pixels. A sentence becomes a stack of token vectors. Audio becomes a stream of samples. A user becomes a vector of behavior. Turn the messy, real world into vectors, and a computer can finally compare it, group it, and learn from it. Honestly, half the craft of data science is just choosing how to turn your problem into vectors. So what can we do with vectors? 2 things. The first is add them. And adding is beautifully physical. Walk along the first vector. Then from where you land, walk along the second. Where you end up is the sum. Tip to tail. Underneath, you're just adding the matching coordinates. But the picture is what matters. Adding vectors is how features stack and how separate signals blend into one. The second move is to scale. Multiply a vector by a plain number. Double it, and the arrow grows to twice the length, same direction. Multiply by a half, and it shrinks. Multiply by -1, and it flips to point the opposite way. That is it. Add and scale. Those two humble moves are the entire grammar of linear algebra. Every single thing ahead is built from just these two. Chapter 2. Similarity. And the one operation that powers everything. Before we can compare two vectors, we need to measure one. How long is it? And the answer is an old friend, Pythagoras. The length of a vector, we call it the norm, is just the straight line distance from the origin out to the point. Square the coordinates, add them, take the square root. The same little triangle you met at 14, now working in any number of dimensions at all. Once you can measure length, you can measure difference. Subtract one vector from another and take the length of the gap between them. A small distance means the two things are similar. A large distance means they are different. That is the whole idea behind nearest neighbor search, behind find me more like this, behind clustering. Similarity, turned into a number you can compute. It's all just distance in the cloud. Now the single most important operation in this entire series, and it is almost laughably simple. The dot product. Take two vectors, multiply their matching entries, and add up the results. Two vectors go in, one single number comes out. That is all. Write it down once, because this quite little sum is the most frequently computed operation in all of machine learning. So what does that number actually mean? It measures alignment, how much two vectors point the same way. Watch it live as one vector turns. Pointing together, the dot product is large and positive. At a right angle, it drops to exactly 0. Pointing opposite, it goes negative. So the dot product is a similarity score between directions. And now you can literally see it rise and fall as the angle changes. There is one wrinkle. The dot product also grows simply when vectors are longer. Often you do not care about size, only direction. So divide the lengths back out, and you are left with the pure angle between them, the cosine similarity. It runs from 1 for identical directions, to 0 for unrelated, to -1 for opposite. It is exactly how a search engine, or a word embedding, decides that two things mean nearly the same thing. One more, and it is gorgeous. Projection. Shine a light straight down from one vector onto another, and you get its shadow. How much of the first one points along the second? That shadow is the projection. It looks like a small geometric trick, but it is the silent engine inside linear regression, inside PCA, and inside the attention that powers language models. Keep an eye out for the shadow. And here is the payoff for learning that one little sum. You have already met the dot product everywhere. A recommendation? Your taste vector, dotted with a movie's vector. A single neuron? Its inputs, dotted with its weights. Attention in a transformer? A query, dotted with a key. Recommendations? Neurons. Attention. Dot products, by the billion. Master this one move, and 3 of the videos still ahead of you suddenly click into place. Chapter 3. Matrices. Picking up space and setting it back down. If a vector is a point, what is a matrix? Forget the grid of numbers for a moment. A matrix is a transformation, a machine. You feed it a vector, and it hands you back a moved one, rotated, stretched, reshaped. That reframe is everything. A matrix is not a noun, a passive box of numbers. It is a verb. It does something to space. And here is the beautiful part. It does not move one vector. It moves all of space, at once, in a single consistent way. Watch the entire grid bend together. The basis arrows, ayat and jihat, slide to new homes, and every other point rides along with them. In fact, that is the secret of what those numbers mean. The columns of a matrix are simply the places where ayat and jihat land. Read a matrix and you can see the motion. Change the numbers and you change the motion. But it is always one of a small family. A matrix can rotate space, spinning everything about the origin. It can stretch it, pulling along an axis. It can shear it, sliding layers past each other like a deck of cards. Rotate, stretch, shear, and their combinations. That is the entire vocabulary. Every matrix you will ever meet is just some blend of these. Let's read the multiplication itself, because it is lovely. When a matrix meets a vector, the output is a weighted mix of the matrix's columns, and the vector simply supplies the weights. So often, the move is recombining columns. A neuron does precisely this with its inputs and weights. So does every layer you will ever train. You are looking at the actual machinery now. Each transformation also answers a question. By how much did it change area? Watch the little unit square as space transforms. It grows or it shrinks. That factor is called the determinant. A determinant of 1 means area is preserved, larger, and space expands. And a determinant of 0 is dramatic. Space got flattened, squashed down onto a line. Information collapsed. And, as we will see, that can never be undone. What if you want to do one transformation and then another? Rotate, then stretch. You could apply them one at a time, or you can fuse them into a single matrix that does both in one shot. That fusing is exactly what matrix multiplication is. And this is the quiet engine of deep learning. A deep network is nothing but many simple transformations, multiplied together into one astonishingly rich one. So let me close the loop and say it outright. A layer of a neural network is this. Take your data, multiply by a weight matrix to transform it, add a bias to shift it, then bend it with an activation to add curves. That is the whole formula. Linear algebra is not some prerequisite you suffer through before the real machine learning. It is the material that neural networks are carved out of. Chapter 4. Hidden Structure. The natural access of your data. Now we go a little deeper into the structure hiding inside vectors. Take a few of them and mix and scale them in every way you can. The complete set of places you can possibly reach is called their span. 2 arrows might span a flat plane. 3 might fill all of space. Span is the reach of your features, the precise set of things your model is even capable of expressing. Reach matters. But beware redundancy. Suppose you have 3 feature columns, but the third is secretly just the first 2 added together. It points nowhere new. It adds no fresh direction. The number of genuinely independent directions is called the rank. Rank is the cure for columns that look informative, but quietly repeat one another. Exactly the kind of hidden redundancy that can mislead a model. Here is a place this all pays off. A system of linear equations, several unknowns, looks like algebra. But geometrically, you are just asking one thing. Which single point lies on all of these lines at once? Where do they cross? That picture instantly tells you whether there is exactly one solution, none at all, or infinitely many. Geometry turns a wall of algebra into something you can simply look at. If a matrix performs a transformation, can we undo it? Usually, yes. With its inverse, which rotates and stretches space precisely back to where it started. Transform, then inverse transform, and you are home. But remember the determinant of 0, where space got flattened onto a line. There is no inverse for that. Once dimensions are crushed together, the information is gone for good. Some moves simply cannot be reversed. Now, one of the most beautiful ideas in all of mathematics. When a matrix transforms space, most arrows get knocked off into a new direction. But a special few refuse to turn. They only stretch or shrink, staying perfectly on their own line. Watch them hold their ground while everything else swings around them. Those unmoved directions are the eigenvectors, the natural, built-in axis of the transformation itself. And each eigenvector comes with a number, how much it stretches. That number is the eigenvalue. A large eigenvalue marks a dominant direction, where the transformation pushes hardest. These are not abstract curiosities. Eigenvectors and eigenvalues are the secret behind how Google first ranked the web, behind the stability of systems, behind vibration and resonance, and behind the very idea on the next slide. Real-world data is rarely a neat, round blob. It stretches, spreading far along some directions and barely at all along others. Principal component analysis finds those directions of greatest spread. Watch the main axis swing 2-point the long way through the cloud. That is the first principal component, and it captures the most variation. The next one captures what is left, and so on, ranked by how much each explains. And here is why anyone cares. Once you know which directions carry the real spread, you can throw the flat ones away, and the points barely move. Watch them collapse onto fewer axes, almost unchanged. That is compression. 1,000 noisy, tangled columns squeezed down to a handful of meaningful ones, with almost nothing lost. Same data, far less clutter. That is eigenvectors, quietly earning their keep. Chapter 5. Probability. Giving the world's uncertainty a shape. We turn now to the second language, chance, and it rests on one humble number, somewhere between 0 and 1. 0 means it never happens. 1 means it is certain. A half is a coin flip. Here is the mindset shift. A good model almost never says definitely. It says 80% likely. Probability is the language of honest confidence, because the real world only ever hands us partial, incomplete information. When a number is uncertain, a dice roll, tomorrow's demand, a noisy measurement, we call it a random variable. And the full description of it is its distribution, a shape that tells you which values are likely and which are rare. Do not picture a single answer. Picture the whole shape of possibilities. Because in statistics, the shape is the entire story. Get the shape, and you understand the uncertainty. And one shape rules them all. The bell. Heights, measurement errors, the noise in a sensor, test scores across a city. Astonishingly many things pile up near a central average and thin out smoothly on both sides. This is the normal distribution, the bell curve, and it is the single most important shape in all of statistics. We will keep coming back to it, because nature keeps coming back to it. The bell is pinned down by just two numbers. The first is the mean, the center, the balance point. Slide the mean, and the whole curve glides along with it. It is also called the expected value, the long-run average you would get if you repeated the experiment over and over, forever. When someone says on average, this is the precise thing they mean, the point where the distribution balances. The second number controls the width. Watch the bell breathe, wide, then narrow. That spread is the variance, and its square root, the standard deviation. Low variance means tight, consistent, predictable. High variance means wild and scattered. Hold tight to this word, variance, because it returns later as nothing less than the central tension at the very heart of machine learning. Now connect to uncertain things. When one is high, does the other tend to be high too? That relationship is the covariance, and its cleaned up cousin, correlation. Measure it for every pair of features, and you assemble the covariance matrix. And here is a quiet thunderclap. The eigenvectors of that very matrix are exactly the principal components from the last chapter. Two ideas you met separately were the same idea all along. Finally, the move that lets us learn from evidence. New information changes the odds. The probability of rain is one number. The probability of rain, given that the sky just turned dark and heavy, is a different, larger number. We write it with a vertical bar and call it conditional probability. Updating your belief the instant a clue arrives. That small bar is where all learning from data quietly lives. Chapter 6. Statistics. What a noisy glimpse reveals about the whole. Here is the catch that defines all of statistics. You never get to see the whole truth. You cannot measure every customer, every voter, every atom. You get a sample, a small, noisy glimpse of a vast, unseen population. So everything in statistics circles one careful, almost philosophical question. What can this little handful of data honestly tell us about the whole, and exactly how sure are we allowed to be? And now, the single most magical fact in all of statistics. Take a sample, average it. Take another, average that. Do it again and again, and plot all of those averages. Here is the miracle. No matter how strange or lopsided the original data was, those averages always pile up into a bell. Watch the order emerge from the chaos. This is the central limit theorem, and it feels like a law of nature, because it nearly is. Why does that one fact deserve to be called a superpower? Because the bell is completely described by just two numbers, its mean and its spread. So the central limit theorem lets us put honest error bars on an average. It lets us run an A to B test and know whether the result is real. It lets a poll of a few thousand people speak reliably for millions. It is the sturdy bridge from a little bit of data to genuine confidence. But confidence has a price, and it is worth knowing. Gather more data, and your estimate gets tighter. Watch the bell narrow as the sample grows. The width, the standard error, shrinks like 1 over the square root of the sample size. Read that carefully. To halve your uncertainty, you need 4 times the data. It is the law of diminishing returns, made exact. And it is why the very first 1,000 examples are worth far more than the next. Let me show you how badly intuition can fail with a famous trap. A test for a disease is 99% accurate. You test positive, so you're almost certainly sick, right? Watch. The disease is rare. Only one person in 100 truly has it. Among the other 99, that small error rate still produces a scatter of false alarms. Count them up, and the false alarms swarm the single real case. Test positive, and you are still, most likely, perfectly fine. That was not a paradox. It was just forgetting where you started. Bayes' rule makes it precise. Take your prior belief, multiply it by how well the new evidence fits, and you get your updated belief, the posterior. You update, you do not replace. The rare disease trap only stung because we ignored the prior, that the disease was rare to begin with. This single rule is how a rational mind and a humble spam filter actually learn from the world. One last warning, and it may be the most important sentence in the whole video. Correlation is not causation. Ice cream sales and drownings rise and fall together. Not because cones are dangerous, but because both follow the summer heat. Two things, moving in lockstep, might share a hidden cause, or be sheer coincidence. The single deadliest mistake in all of data science is mistaking a pattern for a reason. Stay suspicious. Chapter 7. Calculus. Quietly, the answer to one single question. We arrive at the third language, change. And I promise you, all the fear around calculus boils down to one question. If I nudge the input just a little, how much does the output move? That is the whole thing. That sensitivity has a name, the derivative. Forget the thick textbook, the integrals, the tricks. This one question is the entire reason calculus earns its place in machine learning. And the derivative has a wonderfully simple picture. It is just the slope of the curve at a point. Watch the tangent line ride along. Where the curve is steep, the slope is large. A tiny nudge changes the output a lot. Where it flattens, the slope shrinks towards zero. That is all a derivative is. The local steepness and direction of a curve, read off at the exact spot you are standing. And that little number tells you two things at once. Its sign tells you which way. Positive. The curve is climbing. Negative. It is falling. Its size tells you how fast. A big number means racing. Near zero means nearly level. Hold both of those together, and you can already feel the next idea forming. If you want to go downhill, you simply step against the slope. We are one step from how machines learn. Here is the first prize calculus hands us. At the very bottom of any valley, at the best possible setting, the curve is momentarily flat. The slope is exactly zero. Watch the ball settle, and the slope vanish. So the vague, enormous goal, find the best model, quietly transforms into something sharp and solvable. Find the place where the slope is zero. Calculus just turned a wish into a target. Real models do not have one knob. They have millions. So we ask the very same question. Once per knob. If I nudge only this single weight and freeze all the others, how does the error change? That 1/time slope is called a partial derivative. It sounds fancy, but it is the identical idea you already own, just aimed carefully along one axis, while everything else holds perfectly still. Now gather every one of those partial slopes, one for each weight, into a single long list. That list is the gradient. And notice, with a smile, that it is a vector. The languages are folding into each other. The gradient is a vector that points in the direction which makes the error climb the fastest, the single steepest uphill direction across millions of dimensions at once. And that hands us the entire strategy on a plate. The gradient points the steepest way up the error. So flip it around, take a step in the exact opposite direction, and the error drops as fast as possible. Measure the slope. Step against it, measure again. Step again. Repeat. That simple, relentless rhythm is how every model on Earth learns. And on the next chapter, we finally get to watch it happen. But one piece remains. With millions of tangled weights, how do you get all those slopes efficiently? The answer is the chain rule. And its picture is simple. If x nudges h and h nudges y, then the effect of x on y is just the two little slopes multiplied together. A neural network is one long chain of these links, and multiplying the effects back along the chain is exactly how it learns. Remember this picture. It returns with a famous name, backpropagation. Chapter 8. The Synthesis, where all three languages turn together. Let us assemble everything into the single most important idea in machine learning. Picture the model's error as a vast landscape. Every possible setting of the weights is a location on that terrain, and the height at each spot is how wrong the model is there. Good settings sit in low valleys, terrible ones on high peaks. With that picture, training becomes one clean sentence. Find the lowest valley in the landscape. And how do you find the lowest valley, blindfolded, in a space of billions of dimensions you could never hope to see? You roll downhill. You cannot view the whole map, but you can always feel the slope right under your feet and step the way it falls. Watch the loss drop with every step. That is gradient descent. That is the engine. Strip away every buzzword. And this is how machines learn. One dial decides whether it works at all. The size of each step, the learning rate. Step too timidly, and training crawls. It may never arrive. Step too boldly, and you leap clear over the valley and bounce up the far side, the error exploding. Somewhere between is the stride that glides smoothly to the bottom. Tuning that single number is genuinely half the day-to-day art of training models. And the leap to real models takes nothing new at all. Here is the same descent, shown from directly above, contour rings around the minimum, the ball stepping inward along the slope each time. Now imagine not two dimensions, but millions. The picture is identical, only the number of axes changes. Step, recompute the slope. Step again, the same humble move, scaled to the size of a brain. Now stand back and watch the three languages of this entire video click into a single machine. You represent the data as vectors and transform it with matrices. That is linear algebra. You measure how wrong you are as a probability or a loss. That is statistics. And you improve by following the gradient downhill. That is calculus. One loop, three languages, turning together over and over. And the quiet shock is that this one loop trains essentially everything. A two-line linear regression. This loop, a deep neural network. This loop, ChatGPT, with its hundreds of billions of parameters. Astonishingly, the very same loop, represent, doubt, improve, just scaled almost beyond imagination. Once you truly see it, you cannot unsee it. It is sitting underneath all of modern artificial intelligence. Chapter 9. The Mindset and What You Are Free to Ignore. Before we close, let me lift a weight off your shoulders by naming what you can simply skip. You do not need to grind through proofs and theorems. You do not need to compute integrals by hand. The computer does every derivative and every multiply for you, instantly and perfectly. What you do need is the intuition, knowing what each picture means. Read the pictures. Let the machine do the algebra. And here is the kindest learning strategy I know. Do not try to master all of this upfront, in order, before you are allowed to begin. Start building something real. The moment you slam into a wall, a gradient you do not get, a covariance, a projection, go and learn that one piece, right then and there. It sticks effortlessly, because now you can finally see what it was for. That is just-in-time learning, and it beats a year of theory with no purpose. So let's hold the whole video in 3 short breaths. Data is space, vectors and matrices, points and transformations. Uncertainty is chance, distributions, the bell and base. And learning is change, slopes, gradients, rolling downhill. 3 pictures, 1 loop. That, and not a PhD, is the real mathematics of machine learning. Here's the truth I most want you to carry out of this. The wall was never really there. What frightened you off was the notation, the dense, alien symbols, not the difficulty underneath. Because underneath those symbols sit 3 simple, visual ideas that you can now genuinely see. Hold them, and the rest of artificial intelligence quietly opens its doors. Because every model you will ever meet is built from exactly these 3. You now have the language. In the next video, we set it loose. That same represent, doubt, improve loop becomes machine learning itself. Fitting functions to messy data, measuring them honestly, and keeping them from fooling themselves. The mathematics you just met is about to stand up and come alive. I will see you there. If this finally made the math click for you, there is a whole series like it on machine learning, deep learning, and the ideas behind modern AI. Follow along and keep that curiosity burning. I will see you in the next one.